When astronomers look out into the deep cosmos, they see galaxies rushing away from us faster every day. We call the invisible driver of this accelerating expansion dark energy. Since the time of Albert Einstein, physicists have largely modeled this energy as a steady, unchanging pressure pushing the universe apart, the cosmological constant. Recently, however, the DESI collaboration reported findings that suggest dark energy's equation of state might not be a fixed number, but something that shifts as the universe ages. If the strength of dark energy isn't a constant, then the simple, steady universe we've modeled for decades no longer fits. It would mean our current math for the trajectory of the cosmos is built on a premise that may not hold up. The problem is, dark energy is invisible. We can't observe it directly. We can only infer its properties mathematically by studying massive, incredibly complex datasets. When a dataset suggests a conclusion that alters our basic understanding of physics, the methodology has to be flawless. We have to know if DESI's measurements are truly robust. Before we move away from our established models, we have to audit the raw data that generated this new claim. That is exactly what researchers Samsuzaman Afroz and Suvodeep Mukherjee set out to do. They decided to stress test the evolving dark energy claim by pitting its foundational datasets against each other. The first dataset acts as a cosmic ruler. We use the blinding explosions of distant supernovae as standard candles, measuring how fast they move away. The second dataset measures baryon acoustic oscillations, or BAO. These are ancient, frozen ripples in the density of visible matter, generated by acoustic waves in the primordial plasma right after the Big Bang. While supernovae and BAO track the exact same universe, they calculate distance using completely independent methods. That makes them perfect tools to cross-check one another. To perform this cross-check, Afroz and Mukherjee needed a control variable, a foundational rule that holds true under general relativity. They found it in something called the cosmic distance duality relation. This diagram models how the rule works. If you have two independent tools measuring the exact same cosmic distance, they must intrinsically connect. Their mathematical results must synchronize completely. Therefore, if the measurements pointing to evolving dark energy are sound, the underlying datasets must perfectly satisfy this duality relation. The team ran the massive supernova datasets and the DESI BAO measurements through the duality test to see if they matched. At first glance, they are broadly consistent. But looking closely, this graph shows the two lines separating, a minuscule mismatch. As we scale out to the universe's edge, this tiny error widens, drastically distorting our timeline of cosmic expansion. If the foundation is misaligned, any complex calculations built on top of it will be skewed, including the behavior of dark energy. Afroz and Mukherjee then mapped the precise size and shape of this data mismatch directly onto the DSI parameters that first suggested dark energy was evolving. The anomaly perfectly correlates with the systemic error. The evolution we thought we saw isn't a physical change in the cosmos, it is a discrepancy inside the instruments themselves. The researchers concluded that the evidence for dynamical dark energy is effectively absent. The classic steady cosmological constant remains our most accurate model. What initially looked like a shift in the laws of physics was actually a phantom signal, born entirely from microscopic misalignments in the raw data. Astrophysics is rapidly entering an era dominated by massive observatories, gathering volumes of information far beyond what human beings can manually parse. Afroz and Mukherjee's auditing technique provides a critical blueprint. Moving forward, teams will use it to estimate and mitigate these hidden systematic effects in upcoming surveys. Until those tools are flawlessly calibrated, it is too early to claim a robust detection of dynamical dark energy. Unlocking the nature of dark energy depends on our ability to guarantee that the foundational data is sound. When you look at the Milky Way, star clusters are broken up by dark, cloudy bands cutting through the center of our galaxy. That cloudiness is actually vast amounts of cosmic dust, creating a massive blind spot in our night sky. Because of that dust, about half of the light coming from the galaxies in our universe is completely hidden from view. This creates a scientific roadblock known as the confusion limit. To understand it, look at this diagram. When observing deep space, distinct light sources from far-off galaxies hit that dust layer and smear together into a single glowing smudge. Because of that blurring effect, astronomers run into a wall. They can detect the light, but they cannot tell if that single smudge is coming from one massive galaxy, 10 smaller ones, or 1,000 of them clustered together. Currently, our best tool for peering through that dust is the ALMA array, a collection of 66 radio antennas positioned in Chile's Atacama Desert. But ALMA has a strict mechanical limitation. It acts like a high-powered microscope. In any given observation, it can only see an area of the sky thousands of times smaller than the surface of the moon. You cannot map the entire sky using a microscope. Relying on such a narrow field leaves us with a biased picture, missing half the universe without a wide enough lens. To fix that blind spot, a new European-led coalition is returning to that high, dry, and pristine atmosphere in the Atacama Desert. They are designing the Atacama Large Aperture Submillimeter Telescope, or AtLAST. If ALMA is a microscope, AtLAST is a wide-angle camera, engineered to capture submillimeter radiation across the whole sky. This scaled outline shows exactly what it takes to get that wide-angle view. AtLAST requires a 50-meter primary dish and a 12-meter secondary mirror. The entire steel and aluminum structure will weigh roughly 4,400 tons. Despite weighing as much as a freight train, that entire structure has to move, sweeping back and forth across the sky incredibly fast to actively map the sky. By combining that massive surface area with high-speed sweeping, a single AtLAST observation will capture an area 16 times the size of the moon. The microscope limitation is entirely eliminated. But building a 4,400-ton machine creates an immediate engineering problem. How do you run a power-hungry, high-speed observatory in a remote, high-altitude desert without relying on fossil fuels? The engineers solved this by designing the telescope to run like a giant hybrid car. As the dish slows from a sweeping motion, it brakes, recovering kinetic energy as electrical charge for an onboard battery bank. This energy is combined with solar power and metal hydride storage to create a self-sustaining grid tailored to its movements. The project even plans to use near-zero carbon power to manufacture the raw steel and aluminum needed for the dishes. The researchers hope this design sets a pattern for future megascience, showing that even a power-hungry 50-meter class observatory can operate within the limits of Europe's climate targets. With the power and mechanics sorted, the focus shifts back to the sky and to the data this wide-angle lens will actually capture. By tearing through the confusion limit, astronomers project AtLAST will uncover up to 50 million previously hidden galaxies in just 1,000 hours of observation. Mapping those missing galaxies allows researchers to locate the vast reservoirs of cold gas and dust that act as the raw fuel for star and planet formation. By peering into the debris disks surrounding young stars, the telescope will also be able to spot specific molecules, giving us a direct look at the chemical building blocks of life as they form. Plotting 50 million new data points across the sky gives physicists the density maps they need to measure the gravitational pull of dark matter and to calculate the accelerating expansion of the universe driven by dark energy. And unlike disposable tech, AtLAST is designed to do this long-term. The facility features an upgradable instrumentation bay to keep it operational for at least 50 years. Linking what our other giant observatories see to this new map of cold gas and dust, AtLAST provides the data needed to observe the full evolution of galaxies across cosmic time.